Okay, everyone, thank you very much for coming. So today we have the pleasure of having Richard Nally coming from Cornell. He's going to tell us a bit about a series of papers he's been working on, all around sort of the idea of landscapes of supersymmetric AdS Vacua. Thank you, Richard.
Thank you, Edward, and then thank you for to the organizers for having me. I appreciate it. So yeah, I'm going to tell you about some work in progress with the Cornell group on constructing supersymmetric AdS vacua of string theory and some associated techniques we've had to develop along the way. And why did my cursor go up? I'll click from here. Yeah, so here are my collaborators. And so one of the questions that live at the heart of string phenomenology is, does string theory have vacua that resemble our universe? But the problem is the landscape of string theory, the set of solutions to Calabi-Yau compactification of string theory, is just so big that you could never hope to enumerate them all. So questions like, does string theory have a vacuum with our observables and our parameters is just way too difficult of a task to answer. So as a baby version of this question, as a necessary first step to try and construct us and string theory, one could ask, does string theory have de Sitter vacua? And this is a question that's had a great deal of argumentation. There is a proposal from KKLT for how to do it, and then there have been many papers over the last 20 years that have addressed various questions about the KKLT mechanism, and then there's a community called the Swampland, which has grown up largely around asking this question. And so our idea basically was, instead of having all of these arguments, let's just build an example. Let's see if we can find a single example meeting all of the criteria laid out for KKLT. And then on top of this example, people can explore their questions in very concrete detail. So today I'm going to tell you about building a vacuum that has one single vacuum that has all of the necessary ingredients for KKLT. And in order to do this, we'll have to take one small corner of the string theory landscape and flesh it out in excruciating detail. And as a one-sentence summary of what's going to happen today, I'm going to give you the first example of a supersymmetric AdS flux vacuum located exponentially close to a conifold point in moduli space, where all moduli, complex structure, Kähler moduli, and the axiodilaton are stabilized. And this is the core results of our first paper, which should be coming out in a few months. And so the basic context for this work is Calabi-Yau compactification of 2B string theory. So 2B string theory is a 10-dimensional theory. So to make contact with our 4-dimensional universe, we compactify on a Calabi-Yau threefold, which is a compact Ricci flat Kähler manifold. And the reason why we pick this is twofold. One, a 4-dimensional flat space times a flat 4-dimensional 6 manifold solves 10-dimensional Einstein's equation, which is the basic content of 2B string theory. And the other reason why you do this is, if you just work in the 4D effective field theory, Calabi-Yau compactifications preserve some of the supersymmetry. Each choice of Calabi-Yau threefold gives you a 4-dimensional n equals 2 supergravity effective field theory, and the matter content of the field theory, the amount of scalars and fermions you get, is determined by the Hodge numbers of the Calabi-Yau. And in particular, we have many massless scalar fields corresponding to what are called the moduli of the Calabi-Yau, which are some parameters that determine the size and shape of the Calabi-Yau. So there's three basic types. The first one are the complex structure moduli. These are the ones that determine the shape of the Calabi-Yau. The simplest example of a Calabi-Yau, it's a one-dimensional object, not a three-dimensional object, but it has all of these same ingredients, is a torus. And you can have a fat donut or you can have a skinny donut, and that's what we call the shape of the donut. And the second kind of modulus is a Kähler modulus that controls the total size of a Calabi-Yau. For a Calabi-Yau, there's always one representing the total size. And you can shrink your donut, you can grow your donut, and that's a Kähler modulus. And finally, there's one more called the axiodilaton, which controls the coupling constant of the supergravity theory. And for many purposes, you can think of the axiodilaton as a complex structure modulus. But there's a problem, which is that the real world, so us, doesn't have hundreds of massless scalar fields floating around. So what we try to do is we want to stabilize the moduli. We want to introduce some potential for the moduli viewed as a classical field theory, such that the moduli find a minimum to live in and live in this minimum and effectively get a mass. And that's called moduli stabilization. And the way we're going to do this is we're going to do what's called a flux compactification. You add extra ingredients to your string compactification. They break some of your supersymmetry. They give you a 4D n equals 1 effective field theory instead of a 4D n equals 2 effective field theory. But in particular, they also give you a potential for the moduli fields. And this is an example of what one of these potentials could look like. And there's a very nice minimum here. The moduli fields sit at the bottom of the minimum, and then they're no longer hundreds of massless scalars floating around. And one way of asking the question of the string landscape is to say, what minima are possible in the class of effective potentials determined by flux compactification? And that's the approach we're going to take today. We're going to build many of these effective potentials. We're going to build, one slide I'm going to talk about an ensemble of billions of effective potentials, and we're going to study what kind of minima they have. And so this is the form of the effective potential for the scalars in string theory. And it's a fairly complicated function. It's a function of hundreds of complex variables, but it's built out of two simpler functions, two auxiliary functions called the superpotential and the Kähler potential. And the task in front of you, if you want to build string compactifications, is you want to construct these two things, the superpotential and the Kähler potential. And both of them, the superpotential and the Kähler potential, depend on both types of moduli, the complex structure moduli and the Kähler moduli. And mostly today, I'm going to be talking about the superpotential, but the Kähler potential will keep on appearing. And so today we're going to talk about the simplest class of solutions to this potential, which are called supersymmetric minima. So in supersymmetric minima, this particular combination, the derivative of the superpotential minus the superpotential times the derivative of the Kähler potential, you set that to be 0 for all of your complex structure and Kähler moduli. And this means that the resulting minimum doesn't spontaneously break the n equals 1 supersymmetry of the effective field theory. And importantly, if this guy is 0, then this first term totally vanishes, and the effective potential is negative semi-definite. You can't have supersymmetry preserving minima with a positive potential energy. You can only have 0 potential energy, Minkowski space, or negative potential energy, AdS. And so in particular, today, I'm going to construct supersymmetric anti-de Sitter vacua. And yeah, okay.
At the end, are you going to talk about the relationship of your result to actual KKLT?
Yeah, definitely. That's in like 2 slides. Actually, maybe I'll just say it now so we know where we're going. KKLT is a way of building de Sitter vacua out of supersymmetric AdS vacua. And they argue that if I hand you a specific type of supersymmetric AdS flux compactification, you need to be close to a conifold, and you need to have all of your moduli stabilized. Then from there, they give you a proposal for how to uplift it to a de Sitter. And we're going to construct vacua that meet all of their criteria. Yeah, that's the point of today's talk. Is that all of the ingredients, KKLT is a complicated mechanism, but all of the ingredients will be realized in these examples.
Isn't a lot of the controversy about going and taking that next step?
That's why we're doing this. There are no single example for which you could hope to do the next step. So it's all about guessing parameters and checking. No more guessing parameters. I can tell you what the parameters are.
It's controversy about this step too. So even this step would be in advance. By AdS here, you mean scale separated, or you don't care?
So these are PFVs. So scale separation is, I mean, they're no more scale separated than the AdS KKLT paper, but they have some scale separation.
But they're more, I mean, they're scale separated, unlike Freund-Rubin classifications.
Yeah, sure. Yeah. There's controversy at every step. It's impossible to be in this field and not have controversy. Somehow the sociology arrived such that many people have thoughts, and that's good because it's an important problem. It's an important problem of central interest. I don't really, yeah. The point of string theory is we wanted to describe us, right? We wanted to get us out of it, and this is the field that's actually trying to do that. And because it's such a central question, lots of people have strong feelings, and that's a good thing. Yeah.
I think you're okay so far.
Let's see how long.
We're not yet overly emotional.
Yeah, I haven't left the introduction yet. If I can make it to the introduction without upsetting anyone, I think I will have beat the average string phenotalk. But yeah, by the end, I'm sure I will have said things that will have upset people. Maybe not here, but the global set of people will have been offended by the end. Okay, so this is the general form of the superpotential and the Kähler potential, and the point is that the superpotential is determined by a few choices. First, I have to pick flux vectors, elements of integral cohomology of my Calabi-Yau that tell you how much actual flux you've added. And the choice of fluxes gives you a superpotential that depends on the complex structure moduli and the axiodilaton, but never the Kähler moduli. The Kähler moduli can't enter the flux-dependent part of the superpotential. There is another part of the superpotential that does depend on the complex structure moduli. You pick some set of cycles in your Calabi-Yau and you wrap Euclidean D3 branes on them. That introduces an extra term in the superpotential, this term over here, that depends on, in general, all three choices of moduli. This complex structure, the axiodilaton, and the Kähler moduli. And actually today, in all of our examples, I'm going to engineer cases where the complex structure and axiodilaton moduli don't enter into this last piece. These coefficients, which in general depend on the complex and Kähler moduli, are going to be numbers. Now, the numbers are unknown. They're unknown numbers, but you can prove that they're unknown non-zero numbers. Yeah, and so the strategy, because we've engineered a splitting of the superpotential between complex and Kähler sectors, is going to be first to stabilize all the complex structure moduli, and then do Kähler moduli stabilization on top of these already stabilized complex structure moduli. That's a two-step plan. This is basically what KKLT told you to do. And from this argument, there were some examples recently constructed where all of the moduli were stabilized, but you were nowhere near a conifold point, so you couldn't do actual KKLT. And today, the technical novelty is that we're going to be close to a complex structure point, and that's actually going to make doing Kähler moduli stabilization harder.
So you're truncating the Kähler potential, or there should be a plus ...
There is a plus ... This is the tree level Kähler potential. There's corrections in alpha prime, there's corrections in G string. Corrections in alpha prime can be controlled, corrections in G string are unknown, and I'll mention the unknown corrections a little later. Yeah, but this is just the tree level Kähler potential. I didn't want to drown you in details on it before the end of the introduction.
I don't think you can really control even corrections in alpha prime.
I mean, you can enumerate them and see how big they are.
Okay, we'll come back to it. I don't think that's true.
Yeah, I mean, they're controlled by GV invariance on the big H11 set.
No, that would be true if this were an n equal to Calabi-Yau compactification.
And then you can argue that parametrically the n equals 1 corrections are smaller than the n equals 2 corrections. I agree it's not a completely explicit result, but parametrically they should be suppressed at small G string. And then you can say, is your G string really small enough for that to work? But I think in the real limit of 0 G string, they're clearly 0. And then you can just argue that if G string is sufficiently small, then yeah. Yeah. Okay, so now I want to take just a second to lay out the framework of KKLT to motivate what we're actually doing here. And this is what Jeff's question was getting at earlier, which is how does this play into what KKLT actually does? So far I've told you to pick a Calabi-Yau and some fluxes. This determines the potential. And okay, we're going to claim to find a supersymmetric minimum with all moduli stabilized. You can argue that various corrections will destabilize this, but to the level of approximation we're working, we can completely stabilize the moduli. KKLT tells you that if you give them a certain class of flux compactification meeting these criteria, supersymmetric all moduli stabilized, then they give you a proposal for how to uplift it to de Sitter. But not any supersymmetric AdS vacuum will work. You need a supersymmetric AdS vacuum that's close to a conifold point. And the reason why you need to be near a conifold point is if you're close to a conifold point, your geometry grows what's called a long throat. It grows a long tube at the end of which something is shrinking. You have a conifold. And the claim is that if you throw an antibrain down the throat, if you put it at the very end of the throat, and you have enough flux going down the throat, it will sit there stably. And then the stable anti-D3 brain is what does the uplift. The anti-D3 brain has positive energy. The positive energy takes your AdS to a de Sitter vacuum. This is the argument of KKLT, and I'm not going to talk about anti-brain uplifts. I'm not going to mention anti-brain uplifts anywhere in the talk. I'm not going to claim to do them. Instead, what I'm going to do is I'm going to construct Vacua, which we claim meet all of the criterion for KKLT. And then there you can try doing, on these Vacua, you can try doing anti-brain uplifts, and you can make the various arguments that have been made, both for and against KKLT, very explicit in these actual examples. And that's the point. The point isn't that we've done it. The point is that from our results, you can go and do it. And whatever it is you're concerned about, you can just check in these examples. Sure. And so in KKLT, you start with a supersymmetric AdS vacuum, and you add some positive energy, and it gets uplifted to a de Sitter vacuum. And so we're going to do this. We're going to construct this potential with the minimum associated to it. We're not going to do this. This is what many people have objected to many times. We're going to not do this. Instead, our claim is if you have an objection, you can just check it. Right. And that's KKLT. So we're going to construct all of the ingredients for a starting point for a KKLT analysis, and that's the point of today's talk. So to recap, what you need to do for KKLT is pick a Calabi-Yau and some fluxes. If your fluxes have a supersymmetric AdS minimum with all of your moduli stabilized, and such that your minimum is close to a conifold point, KKLT tell you that adding an anti-D3 brain will give you an uplift to AdS. And as has been alluded to, there's been a lot of arguments. I've just cited a couple papers, but there's hundreds of papers on both sides of this debate. And these are some of the more recent, more influential debates. First, there's the no de Sitter conjecture of Vacua and friends. Then there is the so-called singular bulk problem, which says that if you do KKLT, you can never end up in a regime of parameter space where supergravity approximations can be trusted. And then finally, most recently, there's been a proposal by Lust, Wiesner, Vacua, and Zhu that claims to be, it's a holographic argument that claims KKLT can never work. And I have one slide mentioning their proposal later, so I thought I should cite them now. There have been many, many more arguments, and our claim is just that from our results, you can go and make your arguments precise. I don't know what the outcome is. Maybe the outcome is from these constructions, you can never do a KKLT uplift. Maybe the outcome is no, doing KKLT uplifts is easy, but now we can actually just check instead of argue.
I think you're downplaying it. You're presenting presumably the first scale-separated example of AdS. There is no credible scale-separated example until we see it.
What does scale-separated mean?
Scale-separated means the AdS length scale is much larger than the length scale of the internal space.
If you believed that the Cornell group paper from 21 constructed scale-separated Vacua, then they constructed scale-separated Vacua already. If you don't believe they did, then you're not going to believe that I did.
Okay.
So I don't want to claim first scale-separated vacuum, because either you believe they already came into existence or you don't. But these are the first scale-separated. These are the first conifold Vacua with all moduli stabilized. Yeah.
I mean, there are plenty of AdS Vacua with all moduli stabilized. That's supersymmetric. But not scale separated.
Not scale separated. Yeah, sure. But right. But
like AdS 5%.
Yeah.
Like
sure.
Every example of AdS, almost every example we know is of that type.
Sure. So the scale separation is important, but what separates this construction from the earlier construction is well, there's two things. First, we're near the conifold point, so you can do KKLT. So that's why I've been emphasizing the conifolds. That's the real new thing. But also there, they had super small W naught, like 10 to the minus 60. Yeah. Here, ours is like 10 to the minus 2 or 3. And that will make doing Kähler moduli stabilization much harder.
Much harder, okay. Okay.
So those are the big differences from the existing work. Okay, and so like I said, today I'm going to tell you how to do all of the steps leading up to where they tell you to add a D brain to, but I'm not going to talk about adding anti-D3s. So for the rest of the talk, we're going to go through these steps one by one. And in order to In order to actually do this construction, we had to develop a large amount of machinery. Actually, the machinery was developed for a different project, and this was a fun application of the machinery. But I'm going to lay out some of the fun machinery and results we've had to build to get here. Yeah, so that's the point of today's book. So let's start at the very beginning by picking a Calabi-Yau. So every time, for all of the talk today, I'm going to work with Calabi-Yau threefolds that are obtained as hypersurfaces in toric varieties. This is a particular subclass of Calabi-Yaus that we work with only for ease of use. There's nothing special about them. We don't think they really have any properties that make them particularly great, other than in these Calabi-Yaus, you can do calculations, practical calculations, very straightforwardly. There are math papers called Construction of a Calabi-Yau with Hodge numbers blank and blank, and they spend 30 pages proving that some object exists and don't tell you anything about it. That's the opposite of this. These are guys where everything is, you can just get your hands on the data you need very explicitly. And so the way to do this was developed by Batreev in '93, and you start with a 4D reflexive polytope. You triangulate your polytope, and this gives you a Calabi-Yau. And then properties of the Calabi-Yau are controlled by the combinatorial data of this polytope. The appropriate polytopes are classified, and there is just about 500 million polytopes. And all Calabi-Yaus built from these polytopes have Hodge numbers bounded from above by 491. So today we're going to work with Calabi-Yaus whose H21, the number of complex structure moduli, is between 3 and 7. And we're not cutting on H11. H11 is whatever it wants to be. The exact number is determined by the polytope in the Kreuzer-Skarke list, and we're not putting in any cuts. I think the biggest one that I will, we don't get all the way up to 491 because 491 is H21 equals 11. So it's outside of the window where we're looking, but yeah, we're not doing any actual cut on the other Hodge number. And there is a software package developed by some very computationally minded folks in the Cornell group that makes these calculations very easy. So here's our little CY tools mascot. And if you want to do toric Calabi-Yau calculations, you got to use CY tools. So here's what you do. You open the Kreuzer-Skarke list and you just start scanning over Calabi-Yaus. And you immediately run into a problem, which is just there's just too many. You make all of the Calabi-Yaus with H11 equals 3. And you do some calculation to each of them, and you look at the result of the calculation, and you get a bunch of copies of the same information. There are many Calabi-Yaus in the Kreuzer-Skarke list that are redundant, that look like from the toric construction, they should be Calabi-Yaus, the same Calabi-Yau, but are secretly the same. And this is bad if you want to do large-scale computational searches because it leads to redundant efforts. You do, a 24-hour run of some calculation on some Calabi-Yau on your service, and you get the exact same list of information that you've already gotten. You just have wasted a bunch of your time. So one thing that we want to do is we want to cut down the actual landscape. We want to know how many real Calabi-Yaus modding out by these redundancies are there in the Kreuzer-Skarke list. And as is so often the case, mathematicians have already solved the problem, but not in a way that's useful. There's a classification theorem due to Wall, which gives you necessary and sufficient criteria for two Calabi-Yau to be the same. They have to have the same Hodge numbers, H11 and H21, and then certain topological invariants, which are an integral rank 3 symmetric tensor called kappa and an integral vector C2. There needs to be a single integral change of basis matrix that is invertible over the integers. So importantly, it's an integral base matrix with determinant 1 that takes this kappa to the kappa of the other Calabi-Yau and this C2 to the other C2 of the Calabi-Yau. And this theorem exists, and you might think, okay, perfect. This theorem will let you get rid of all of these redundancies. The problem is that it's horribly computationally intractable. You can build 830 Calabi-Yaus at H11 equals 3 from the Kreuzer-Skarke list, and then checking them, there's just combinatorially many different pairs you have to check for whether this change of basis matrix exists. What we actually did was we used some number theory techniques to pre-filter. We used number theory to tell you when certain Calabi-Yaus cannot possibly be isomorphic to each other. And then using this as a starting point, we were actually able to totally classify the number of Calabi-Yaus at H11 equals 3. There's 830 you can build, and secretly there's only 304 independent ones. So in general, on average, each one of these appears about 3 times. So we've cut down the amount of wasted work by a factor of about 3. It's a fun little result from the math involved, and it's also computationally very useful for doing the sorts of scans that are bread and butter.
Is there any idea as to roughly like how the number of inequivalent ones scale with the total numbers of the
Part of a larger effort to characterize the distribution of topologies by H11. We would love to know the answer to this question. In some ways, that's one of the burning questions we're trying to answer, and investigations are still ongoing. At H11 equals 3, the problem is particularly easy. At H11 bigger than 3, the number theory helps, but it isn't enough to get you across the finish line. So we're trying to go up in H11. H11 equals 4, we can get the answer to whenever we sit down and do it. Beyond 4, it's going to be a challenge, and we'd like to ultimately go we'd like to see how high we can go and study the scaling behavior of this fraction as a function of H11. But then let me also advertise briefly that there is another approach at the large H11 scale where it's very difficult to get numbers like 830, where we'd like to study just bulk properties of scaling. And that's sort of a very different set of techniques, but we're also working in that land. Yeah, so that's a great question to ask. We just don't know the answer. And I should mention here that we're working with actual mathematicians because this is a question of actual mathematical interest, not just string theory interest. Okay, and I can't help but mention the way we do this, which is from these topological invariants kappa and C2, you can build rational projective varieties. And if the rational projective varieties associated to two Calabi-Yaus are different, then the two Calabi-Yaus cannot possibly be isomorphic. But isomorphism in the category of rational varieties is much easier to check than is there one of these infinite number of change of basis matrices. So you can just check isomorphism in this category, and if they're not isomorphic, then you're guaranteed that they're not isomorphic in the category of Calabi-Yaus. The other way isn't true. You can be isomorphic in the category of rational varieties and non-isomorphic in the category of Calabi-Yaus, so there's still work to do, but the amount of work you have to do is much less than if you don't do this number theory check.
So I've seen estimates, or I periodically query people about estimates for the number of elliptic threefolds with estimates of order 10 to the 3,000 or so. If you restricted to something like H113 in that space, would you expect a massive reduction of that number, or?
But how could they answer that without doing the kind of calculation that he's doing?
Yeah,
I think it's probably counting equivalent vibrations over.
So, but the total space might be still topologically the same.
Well, good. So yeah. So is that something that they've checked?
Right. So there's different questions. One is what's the total number of fibration structures?
Yeah.
That's useful for counting things like what is the number of F theory compactifications. Then there's the number of Calabi-Yaus, and this is we haven't used any elliptic fibration at all. In fact, the elliptic fibration game really comes into effect at big H11. At big H11, you expect everything is elliptically fibered. At 3, it doesn't really have to be. But yeah. Also, those studies usually are for elliptically fibered fourfolds where the numbers are much bigger.
Well, no, even for threefolds, numbers were huge.
For threefolds, the numbers are huge, but yeah. For threefolds, the numbers are huge, but
why aren't you taking a fibration into the story? Because you have to orientifold too. And that requires making a choice of fibration.
Right. So this is a question. This is a question that's before orientifolds or anything else.
Right. But
these are classifying n equals 2 effective theories. Right.
But if you have two Calabi-Yaus with inequivalent vibrations, and you say they're equivalent, they're isomorphic this way, is the orientifold?
It's two different vibrations of the same Calabi-Yau.
Right.
The orientifold is defined at the level of the Calabi-Yau structure. All of the orientifolds I'm going to talk about today are coordinate flip orientifolds.
You say many vibrations for a given Calabi-Yau.
Yeah. Okay. And this is the number of Calabi-Yaus.
Okay.
And then there are other questions like how many Calabi-Yaus are there, which is like, there's a paper by Liam and friends that estimates there's 10 to the 400 and something Calabi-Yaus in the Kreuzer-Skarke list as an upper bound. And that comes from triangulating polytopes. That's the sort of question we're asking now.
Okay. Okay, good.
So at least the small H11 version of this paper will be coming out in the coming months. A large H11 developing story, but yeah. This is I think one of the more fun parts of the overall program because you get to do a lot of fun, interesting math techniques. Nobody, as far as I could tell, had actually thought about viewing these as number theoretic objects, kappa and C2. So yeah, it was a fun little application. Okay, but let me keep going. Let me tell you how to pick fluxes, giving you a supersymmetric AdS flux vacuum with small w naught. So this is not a new story. This is a story that has been developed in the last couple of years. and we're going to follow a story that's existed. So we work at what's called LCS, large complex structure, which is a particular corner in moduli space where we can expand the flux superpotential into a bit that's polynomial in this complex structure moduli, and then another bit that's exponential in the complex structure moduli. And we look for a one-dimensional slice of the combined complex plus axiodilaton moduli space where this whole perturbative bit vanishes and is covariantly constant. And there are criteria for when you can do this. You need there to be two integral flux vectors, M and K, such that basically this combination of M's is integral. A particular rational vector lives in the Kähler cone of the mirror, and that rational vector is orthogonal to the K. And if you have those, then you're guaranteed a one-dimensional slice of complex structure moduli space, and in terms of which this bit and everything built out of it in the full potential vanishes.
Oh, very good. So you're restricting to an honest supersymmetric starting point.
Yeah.
Good.
Yeah. We restrict to
supersymmetric.
Yeah. So there's a supersymmetric starting point, and then we look for supersymmetric solutions on top of that supersymmetric starting point.
Yeah, yeah, but this is not what KKLT did. Oh no, you haven't computed your W naught yet. You're gonna tell us how you're gonna get to that.
That's the next slide.
Okay.
That's the next slide. Yeah. Once I've arranged this perturbative bit to be 0, all that's left are these exponentials.
Oh, sorry. Yeah. When you say instantons here, you don't mean space-time, you mean instantons at the world sheet level.
No, these are world sheet instantons. Yeah.
Okay.
These are world sheet instantons of the 2A mirror.
Yeah, so that's why I take that what I said. So it's not a supersymmetric starting point. The starting point is non-supersymmetric.
No, it's non-zero. Supersymmetric.
No, it's not. If W instanton is not 0,
then it's n equals 1 supersymmetric, not n equals 2 supersymmetric.
No, it's not supersymmetric, period. W equals 0 is the supersymmetric starting point, total W.
No, the total starting point is dW equals 0.
No, you need W equals 0 for it to be
dW equals 0 is a minimum of the.
Is a minimum
of an energetic minimum, but a supersymmetric minimum also has W equals 0.
But that's a fully supersymmetric.
Fully, yeah. Well, okay, so we can differentiate fully supersymmetric from non-supersymmetric.
Sure, but this is supersymmetric in the sense that KKLT tells you to start with the supersymmetric one. Oh, KKLT takes a slightly different order of limits.
No. There's a little bit of verbiage which is confusing. If you're preserving, you're talking about classical physics here at the moment. You're classically turning on fluxes and you're looking for what symmetry is your background preserving.
Yes.
So your background, if W, the total W is not 0, your background does not preserve supersymmetry. If your background preserves supersymmetry, W equals 0. There's a binary choice. There's no in between.
Sure, but
so what you've done is you've split your W into a piece that you're calling W per, plus these world sheet instantons, and you're setting to 0 W per.
Well, I'm setting that to be 0. That's certainly true. But I'm also setting its covariant derivative to be 0.
Your covariant derivative has to be 0 to be at a critical point.
No, it doesn't. Absolutely not.
Oh, that's true. Sorry, that's wrong. That is wrong. That's right. That's right. Yeah. But to be supersymmetric here, you need W equals 0.
Right. So there are two definitions of supersymmetric vacua in the literature. One of them is W equals 0. Another one is just dW equals 0. W equals dW equals 0 certainly preserves more supersymmetry than just dW equals 0.
It preserves more supersymmetry.
It's the level of the classical background.
W non-zero preserves no supersymmetry. Let me make it clearer.
I mean,
there's only Minkowski vacua in this background classically. So you're asking about a Minkowski space-time solution.
I mean, these are GKP vacua. Do you think GKP vacua
are not solutions of string theory? They mistakenly thought you could do what you did on your first slide, which is truncate your Kähler potential to the supergravity terms. The plus ... we discussed always gives you a physical potential that is not 0, and there's always a ...
Right, and you can look for minima to the associated potential you get from those, and they don't.
There is no minima; it just runs away.
I mean, you can just check it in examples. There's still a minimum.
There is no minimum; it just runs away. I should let you continue, but that is completely wrong. GKP had no solutions of string theory in any sense that we normally call a solution, meaning you solve the space-time equations of motion in some approximation. There's no approximation in which what they wrote down was a solution, except W equals 0. if you want, I'll explain to you in more detail afterward, but it's crystal clear. There is no ambiguity about that statement. What you can do is pretend you have a solution by ignoring the space-time potential. And we can play that game and see where it goes. But that's what you're doing. And it's important to understand that's actually what you're doing.
Then that's what all string pheno papers in the last 20 years have done.
There's lots and lots of wrong papers written in this field that doesn't change what's actually correct.
Sorry, stop. Hey, are you saying that the F-term equation for the Calabi moduli cannot be solved? Therefore, for the solution to be supersymmetric, W0 should be 0. Is that what you're saying?
Yes. Yes. If you do the ... and I think we can agree the leading order ... is non-zero, you write down the physical V you wrote down, and you will find that it is not 0 and runs away toward large volume, typically.
Well, to make you more happy, you can think of it in the following way. So at the level of the superpotential, we are finding exact 0. And then what you'll find, what Richard will presumably tell you is that in the later, that W instanton that is written here is of the same scale as W instanton generated by the actual D instantons. And then they're actually competing. And then, so at the level of the, yeah.
I'm happy to wander off shell from a starting point that makes sense. And a starting point, if you tell me your starting point is W equals 0, that makes sense as a solution of string theory. Then you can try to explore the off-shell physical potential, which is what you want to do, to look for minima. And then you can tell me W instanton is as important as, say, a space-time instanton contribution. That's all fine. But a starting point should make sense at the level we understand.
So is your particular objection to the Kähler potential or the superpotential?
Well, I object to truncating the Kähler. See, you would think this is a solution if you truncate the Kähler potential to just no scale. But that is completely wrong. That is a completely wrong exercise to do because you already missed the terms important for having this thing exist in the first place, being able to turn on the tadpole. You need higher derivative terms to cancel the tadpole. So there is no consistent truncation to no scale in these backgrounds. There's no consistent truncation to supergravity because there are no supergravity solutions that are compact with flux. So you must include ... at least a couple of terms. And those give you a potential.
I mean, you can check vast numbers of these terms and check that the minimum that still exists is still there.
Minimum. There's no minimum for the Kähler potential, for the Kähler module. Okay.
With this Kähler potential, there exist minima for the Kähler module. One can then study the leading correction, what we believe to be the leading corrections to this potential. With the classical tree-level Kähler potential, you can stabilize the Kähler moduli.
Okay.
You can then study what we think are the leading corrections and study how the minimum that exists with the leading potential moves, and it doesn't.
I wrote a paper trying to explain this in gory detail, and I still don't understand why this point is not clear. As we understand string theory today, you usually have to start with something that is a solution in some approximation to the space-time equations of motion, meaning 0 potential energy. You can't be running somewhere. These backgrounds that are Calabi-Yaus or interfolded, where you try and turn on flux, do not exist unless you take higher derivative terms into account. That's the first basic statement.
So one thing that I'd like to remark is that when W0 is really small, although you're correct that the solution is actually a runaway, but then because the runaway is so slow, approximately we can approximate that like the solution or the runaway is behaving as good as a vacuum, and then we can do some approximation around that. Of course, one can say that, oh, I wouldn't take this and I'd only accept exactly a vacuum solution. I think that's a respectable position, but here we're assuming that the runaway is extremely slow so that we can do a reasonable perturbation around it.
So the problem you're going to run into is, I actually buy that argument when it comes to computing loop corrections to the potential, but I don't buy that argument when it comes to making claims about non-perturbative corrections, which is what you're going to do, I suspect.
You mean the Kähler non-perturbative corrections, or these?
Yeah, any non-perturbative things you add to W beyond, yeah, even these things. I mean, no, these things are probably okay. But
this is just mirror symmetry. This is nothing novel.
It's mirror symmetry and using an n equal 2 result for an n equal 1 theory.
It's n equal 1 theory with exponentially small w naught.
Let's continue, and
Yeah, we can. Let me finish, and then we can talk about this offline. But and you can engineer this part to be 0, and you can engineer everything that comes from that part in the scalar potential to be 0. And then what's left with is these instanton guys. And from these instanton guys, it's actually not very hard to engineer for a supersymmetric solution to the whole complex structure potential just by setting the covariant derivative of this instanton series to be 0. In the cases we're going to consider, this guy is dominated by 2 terms. So your effective superpotential is just 2 competing exponentials, and like you can just solve the equation dt of this equals 0. And you get a supersymmetric minimum at this point in tau space with this w naught. And the point is, this w naught is exponentially small because of this exponential effect.
so this special tau is very light in the theorem. What kind of mass does it have?
The tau is not very heavy. So they're not fully scale separated because of this PFE.
Is it exponentially light compared to the other complex structure moduli?
It's certainly lighter than the, yes, it's much lighter than the complex structure moduli, but it still has a stable minimum to its potential. Hold that question about how the other Kähler potential, how it scales relative to the other moduli for 2 slides from now, because that is making my life brutally difficult in another project. Okay. Sorry, this is important. So maybe let me take 2 more minutes talking about it. We have reduced the whole very complicated flux superpotential to 2 terms, these 2 competing exponentials. So the whole structure, and sorry, I should have emphasized this more earlier. There's a line in the H21 + 1 dimensional complex structure plus Kähler moduli space where this happens. So I have I've integrated out the complex structure moduli and replaced them with just the axiodilaton along the line z is equal to p tau, where p is this guy. So I have a 1-dimensional slice of my complex plus axiodilaton moduli, along which this condition is true, and all we're left with is a 2-term instanton racetrack. You then stabilize all of the complex structure moduli by stabilizing just this tau. That's the game you play, and there's a concrete answer you get. And we now have millions of examples of Vacua of this form, where I can stabilize all of the complex structure moduli for free. And you can start looking at distributions of W naught and distributions of the string coupling and all of these guys. And yeah, we have billions of PFBs of solutions of this form. And you can construct tens to hundreds of millions of supersymmetric AdS Vacua. Yeah.
You compute Gopakumarasa?
Yeah, compute GB merits. Yeah.
Sorry, where's the AdS coming from? At the moment, you've just done worksheet stuff, right? I mean, it's all classical, no? Initially, where's the AdS?
Minus 3W squared. V is.
Don't you have to add a space-time instanton to get a minimum?
As long as you have.
Maybe I'm misremembering something, but I mean, I thought classically there's only Minkowski as a solution.
So that's without the minus 3W squared and the half-term potential.
No, that's with the minus 3W squared. There's only Minkowski.
I mean,
how are you doing this without a space?
W is not 0. If you plug in W not 0, dW equals 0 to the half-term potential, you get a supersymmetric AdS minimum.
Maybe it's like something. One sec. Sorry, where are the Euclidean? There's no Euclidean D3 branes in your story?
I'm not talking about Kähler potential yet. I'm just talking about in the complex structure sector.
Oh, I see. So you say, okay.
The AdS comes from the complex structure sector, and then you stabilize the Kähler moduli on top of it.
Yeah, okay. So, yeah, okay.
This I'm confident I can convince you of because it's like 2 lines of algebra. If you accept the F-term superpotential.
That's okay.
Yeah. I'm not claiming that all of these billions of examples have all Kähler moduli stabilized. I'm just talking about in the complex structure sector.
It's not obvious any of them do. I mean, forget billions. You just need one.
Okay, I claim we have more than one, but we can argue about this offline. Yeah. Okay, and one of the many papers is a detailed application of these distribution of things, and we're going to do our Taylor moduli stabilization technique to these and see, you know, how big of a W naught can you handle on average in a randomly chosen Calabi-Yau, et cetera, et cetera. And the point of this is, in the complex structure sector at least, these SUSY AdS minima are generic. There's something special about them in the sense that, you know, we had to pick a particular choice of flux, but they're there, they're real, they're very common. There's not like 4 of them and each one of them is a precious child handed to you that you must shield with your life. If an order of magnitude of these were killed by some correction that we haven't taken into effect, you know, if 100 million of them went away tomorrow, I would still have another 900 million. So they're very common, is the point I want to emphasize. Now let me make one more comment, which is, you might ask, why do we make a billion of these things? We don't need to make a billion of these things to study distribution of W naught. You can get the same distribution if you kill an order of magnitude. Well, so far I've talked about cases where W instantron only has 2 terms competing. If you allow yourself to have more terms competing, you can have minima where supersymmetry is spontaneously broken. There are real minima of the F term potential that don't have dW equals 0. They're just minima of the potential. And in those cases, you can find de Sitter vacua without any anti-D3 breaks. Yeah, just generated by the fluxes, you can spontaneously break supersymmetry and get de Sitter. And that's just a fact. We have thousands of candidates. This is a real scalar potential from a real PFV and a real Calabi-Yau with the real de Sitter minimum.
Yeah, nothing prevents you from getting de Sitter from a supergravity superpotential generically.
Right.
Yeah. So you're finding cases where
we're finding
all the complex structure are stabilized, and you've got some de Sitter energy that is small, presumably.
We have things that look like that, except there are corrections that kill it. So we have solutions to the PFV theory, the one-dimensional theory for tau, which look exactly like you said. Where, you know, this is the scalar potential for tau, and look, it's got a positive energy minimum. The problem is we had to integrate out all of the other complex structure moduli to get to this effective theory for tau. And when you include their leading correction, they completely destabilize this minimum. It's because they're not heavy relative. In the examples we have, the other complex structure moduli aren't heavy relative to the dilaton. That's the question you asked earlier, is the complex structure moduli relevant to the dilaton? The reason I said hold that question is because in these de Sitter solutions, they're just not. If you include the leading Wilsonian effect from integrating them out, these minima go away. And we don't think that's a fundamental thing. We don't think it can't happen. It's just that generically, if you have a bunch of instantons competing, they end up at pretty mediocre coupling constant. So work is ongoing. We think we know how to get around this, but the solutions we have now that look de Sitter, we've gotten excited about having de Sitter solutions without anti-D branes many, many times, and they always go away. But yeah. We sort of think we know how to get around it by now. It's just hard finding actual examples. De Sitter is a hard problem. Okay, I am not doing so great on time, so let me keep going.
That's my fault. Probably so.
There's been some questions.
Okay, so let me just briefly outline the scheme we use for Taylor moduli stabilization. So the flux superpotential never depends on Taylor moduli, so you need extra terms to stabilize the Taylor moduli. And the way we know how to do it is to think about Euclidean D3 branes wrapping 4 cycles in the Calabi-Yau. So Witten gave you a topological criterion on the 4 cycle for when it gives you a non-vanishing contribution to the superpotential. And it's a certain condition on the Hodge numbers of the divisor inside the Calabi-Yau called rigidity. And Witten proved this was an n=2 analysis, but it's a 0 mode calculation that should be sufficiently robust that it survives once you've broken down to n=1.
This was an n=1 analysis.
Oh, sorry, it was n=1 in the absence of flux.
Yeah.
Sorry, yeah, it was n=1 in the absence of flux. But it's a 0 mode count, and we don't think fluxes can lift universal 0 modes.
No, that's not the problem with that. There's a completely different issue to do with the fact that AdS calculation is pre the realization you needed flux. Pre the realization there was a tadpole. And once you include the tadpole, the physics looks totally different. It's not obvious. These are instantons of any relevance to this actual background.
I mean,
Euclidean space background, for example, that you get with flux is complex. There's a space-time flux also component to the flux, and it becomes complex when you Wick rotate. So it's not at all obvious what the right instantons are, but they're probably not these.
I mean, do you disagree that these instantons contribute to the superpotential?
I do not know what instantons contribute, but that argument is not relevant.
I mean, he computed the partition function of the world volume theory.
Without flux in a background that was
I agree. He did
across Calabi-Yau 4. I know exactly what he did in that paper. And I assure you, if you have a space-time flux, it's a little bit like saying my instantons in Chern-Simons theory are the same as my instantons in Yang-Mills. But they're not. There's a physical difference. When something becomes complex when you rotate, you have to be careful about what saddles contribute. I don't think we really know, to be honest. At least I don't know which saddles should contribute.
For now, let's accept these terms so I can try to get through the rest of my talk. These Euclidean D3 branes induce a dependent. If you believe that these instantons exist, you can compute their contributions to the effective superpotential, and they depend on the Calabi moduli. And so with these guys, they also depend on the complex structure moduli, but there's an additional topological criterion that sets the dependence on the complex structure modulus to 0. And then Witten's calculation tells you that this is the term in the superpotential. With these guys, if you have at least H11 many of these terms, you can hope to stabilize all of your Calabi moduli. And the smaller W naught is, the easier it is to do so. It's because the actual values to which the Calabi moduli get set depend on W naught, and they depend on it in such a way that it works out better if W naught is small. Okay, and using this framework, 5 examples with all moduli stabilized in a supersymmetric AdS vacuum were presented. They were constructed, and you can compute the volume of the 4 cycles. You can compute the Calabi moduli. There is a small problem with these examples, which is that they all had mobile D3 branes, and many people said varyingly polite forms of the following complaint. Everything else is so explicit in your calculations. With the mobile D branes, you kind of just cited previous arguments that it should be okay. Are there examples without any mobile D3 branes, or is there some conspiracy that forces you to have them? There's no conspiracy. There are examples without any mobile D3 branes. You can saturate the entire tadpole with flux and still run this story through exactly as presented. Here's the best example we have at the moment. It's in a Calabi-Yau with H21 equals 4 and H11 equals 214. Sorry, only one of these should be H21. But yeah. And W naught here is 10 to the minus 22. And the examples in the paper, W naught was 10 to the minus 60, but finding those examples took months, and finding this example took me 20 minutes. So yeah. And as part of our forthcoming paper, where we study the distribution of these guys in the landscape, we are going to present examples without mobile D3 branes in case you're concerned about the mobile D3 branes.
Well, I think what I worry about is you even putting aside the other issues that I would have with the story, you have a light tau, right, which is getting a mass from your W naught of order 10 to the minus 22 here. That light tau should presumably also be kept in the Euclidean d-instanton partition function as you go along. So there'll be some non-trivial terms from the sum of exponentials coming from the Euclidean d-term, which is probably going to be bigger than this mass term. How do you know any of this is actually stabilized unless you know the exact dependence?
Well, because we've arranged for the. You mean how do I take care of the tau dependence of the Euclidean D3 brane superpotential?
Yeah, because you've got a tau that is
I've arranged for this coefficient to be just a number.
There's a function of tau.
There's an additional topological criterion that you can show renders this Pfaffian just to be a number.
How is that possible? It's a function generically of the complex structure moduli.
Generically, right? It's based on the intermediate Jacobian of these divisors, and we can arrange the intermediate Jacobian to be trivial. No. This one there is a concrete story for. You're asking about this dependence of tau.
Yeah.
Yeah. You can. There are cases where it's known that this dependence on tau is totally trivial. There's an additional topological criterion for which this guy is not a function of any moduli. It's just a number. It's called pure rigidity. And if I have a pure rigid divisor, these are really just numbers. They don't depend on tau.
Do they depend on any of the complex structure modules?
Nothing. There were complaints that maybe mobile D3 branes induce dependence on the moduli back if you've arranged a pure rigid case, which is why we went and found examples without any mobile D3 branes. But in the absence of mobile D3 branes with pure rigid divisors, this definitely doesn't depend on tau.
That's interesting. And didn't know. Okay. Good.
Yeah, no, this dependence of tau we have taken care of by making it not there. I agree. Generically, you might expect this to overwhelm your PFV, which is why we went through and got rid of it.
Interesting.
And this, by the way, was already in the KKLT AdS paper. So their 5 examples also all had pure rigids.
They had no calculation in the original paper and any background. How could they just made up the superpotential with some numbers?
No. Sorry. This KKLT
paper.
Sorry, AdS. Sorry, we call this paper AdS KKLT in our internal lingo. No. Not original. Sorry. Yes, I agree. Not KKLT. That's the point. Is that KKLT didn't have a Calabi-Yau. Sorry, my bad. No. This. Yeah, no, very good. This paper, which is famously not actually KKLT, but which we call AdS KKLT, to distinguish from Connie AdS KKLT. Okay, great. Let me make one comment here, which is that the proposal by Vacua et al. That came out recently, if I give you a supersymmetric AdS vacuum, a very reasonable question is what's the holographic dual? What's the 3-dimensional CFT whose bulk theory is this AdS string theory? A proposal for the candidate CFT was given by these guys. And their proposal is strictly incompatible with these results. Their proposal requires that the cycle dual to the fluxes be slag, and you can just check that it's not a slag cycle in our example.
What was the proposed CFT?
It's a M5 brane wrapping the cycle dual to the slag. If you want, there's a dual to the fluxes.
A single M5 brane?
Yeah, I believe so.
Probably as many as you need for the flux.
Well, they estimate the central charge from assuming it's a single M5 brane. Their argument has 2 parts. One is these examples of KKLT don't work, and another one is no examples of KKLT will ever work. That one comes from an estimate of the central charge, where they did sort of assume one M5 brane.
The cycle dual
So 1 M5 brane at low energy is a free theory. So what are we talking about?
I think there's a little bit. It's probably a multiply wrapped.
Yeah, sorry, it's wrapped. Yeah.
Or you can think of it as many fibrins as you need to get the dual flux.
Yeah.
The flux is fixed by.
Yeah. They pick the cycle based on the fluxes, and then they try to wrap it to get The point.
How is your dual cycle not supersymmetric in some sense?
Because
you have a supersymmetric classical background. How is it not? Well, sort of supersymmetric classical background.
I mean, you can just check. Even in the W=0 examples, the cycle isn't slag. Special Lagrangian. It's the condition. Sorry, it's the condition for a D brane wrapping a cycle to be super. Yeah. Oh, yeah, that's.
So that's like saying the flux.
I'm confused about what we're talking about here. So we're talking about a CFT3.
Oh, they work in a different duality frame.
They're working.
They work in an M theory picture, and the dimension count works out slightly differently, but it's a dual picture of the same theories.
Yeah, it's so Calabi-Yau 4, M theory and Calabi-Yau 4. But if you turn the fluxes back into branes, which is what they wanted to do, right? Basically.
Yeah, they want the domain wall to be living on a slag cycle.
How are the branes not wrapping something supersymmetric and still preserving SUSY? If the fluxes they classically.
I mean, you can check the following statements. Subject to these approximations, what are the fluxes that give a stable SUSY AdS? And then is that cycle slag? And the answer is no, it's not. But at the level of the this level of truncation, the supersymmetry is preserved.
This is because there's a 4-0 component, presumably.
Yeah, I mean, there are all sorts of topological ways of seeing that this cycle just isn't slack, but I'm not saying their proposal is wrong. I'm saying if their proposal is right, this is what I wanted to say on the rest of the slide. We don't know if their proposal is right or wrong, but they say based on their proposal that these terms can't appear in the superpotential, but subject to Witten's calculation, those terms have to appear. So the exact statement they made is not what's wrong with the theory if there is something wrong. One possibility is that corrections to the Kähler potential destabilize all of the vacua. We don't know, but their precise statement is not correct, even if their conjecture is correct. Right, and one thing we're going to do with our ensemble of vacua, once we've stabilized Kähler moduli in some fraction of them, is just study models for these corrections and see whether they do destabilize you or not.
When you say unknown correction, you're talking about like alpha plane corrections.
G-string corrections to the Kähler potential.
Alpha prime corrections.
Because the alpha prime corrections we already know how big they are. They're not big. They're controlled by mirror GV expansion. They're controlled by mirror GV invariance, which just compute.
Again, not true. This is all based again on using n equal 2 result in a model that's not n equal 2.
It's n equals 2 broken to n equals 1 by small effects, and you can parametrically estimate how big those effects are.
Yeah, the same order as the corrections that the Kähler potential induces. I think I did all these estimates.
If they're in the same order, then we're safe from these corrections.
No, they can still destabilize. Doesn't matter. You're not evaluating on a Calabi-Yau background. You're evaluating on a warped background.
Yes.
With a warp factor whose size you can estimate.
Right.
It's small at large volume. It's not small otherwise.
Right, but we're at large Calabi-Yau volume.
Yeah, you can evaluate it at large volume. But at large volume, it's still enough to generate. I mean, I guess it depends what you mean by conspire to kill these vacua. You mean in terms of not having these superpotential corrections, or on top of that generating a potential?
On top of that generating a potential. I would say if there is one correction that destroys all of these vacua, no matter how small you make W naught, if I really burned my laptop, I could make W naught of 10 to the minus 1,000. If you're saying that regardless of how big that W naught is, these corrections will always kill your vacuum, then I would call that a conspiracy. Instead, what's possible is these corrections sometimes kill your vacua, and then you just need to find solutions where W naught is in the window where they don't kill your vacua. And that I would be totally happy.
I don't understand that thing, because if W naught was 0, any generic instanton is going to roll you away from that supersymmetric minimum. So who cares if W naught is like 10 to the minus billion? It's close to 0. You can expect it to destabilize.
Right, sorry. W naught, no. W naught is the control parameter for this expansion. And the smaller W naught is, the better in control, generically speaking, you expect these corrections to be.
Which corrections are you talking about?
In the Kähler sector. Once you have a stabilized minimum, the control parameter is log W naught. 1 over log W.
I don't understand that. Anyway.
Sorry, this one, again, here I can make what I mean very precise, but let me finish my talk and then I can make it, then we can talk offline. Now finally I can get to the point where I can do all of this with near a conifold. Okay, the PFE condition doesn't work near conifolds because it's based on an LCS expansion. But you can develop a modification to the PFE formalism, which does work near conifold points. It works. You stabilize your conifold modulus exponentially close to the real wall of moduli space where the thing really shrinks. That's good. And you still get small W naught generated by the instanton series as before. That's good. So using this, you have an actual algorithm for finding SUSY Connie AdS KKLT vacua with all moduli stabilized. You start with a Calabi-Yau and you pick a conifold curve in its mirror. You look for PFEs that intersect the wall of the Kähler cone where this mirror shrinks. We have an algorithm for finding PFEs. You find a P that dots to 0 with the conifold curve. Then you find fluxes that support the racetrack with that P. Then you find the supersymmetric AdS minima for the bulk moduli. And if they're in a regime of moduli space where all of the approximations are under good control, then you can try doing Kähler moduli stabilization. If they pass the Kähler moduli stabilization check, then what you have constructed is a supersymmetric Connie-AdS vacuum with all moduli stabilized. And we've done that. We have examples where at the level of approximation we work as well as we know how to check. We claim to as well as anyone knows how to check. These are supersymmetric Connie-AdS vacua, all moduli stabilized. Here are 3 of them. These come from a Calabi-Yau with H21 equals 5 and H11 equals 13. It has one conifold curve in its mirror. From that one conifold curve, we can construct 857 PFVs, 1,857 choices of flux vectors, such that you get this one-dimensional slice of moduli space on which everything is nice. From those 1,900 PFVs, you get 62 solutions that give you supersymmetric AdS minima in the complex structure sector, of which 3 pass all of the cuts you need for the throat to exist and be stable. Here they are. Here's W naught. W naught is 10 to the minus 2 or 10 to the minus 3 in these examples. G string is, okay, this G string is pretty big, but they're around 0.1, or sorry, they're around, 0.05 to 0.1. And GSM, this controls how good the supergravity approximation is. You want GSM to be bigger than 1, so I included this one because GSM is 2 here, but yeah. Many people have argued how big you need this to be. One of the key things we think you can actually check in this example is for these values of GSM, how big are the corrections to the supergravity action? You can just estimate those, and yeah, some people have said you need this number to be 50, and in these examples, you can just check that isn't true. Okay, great. So these are the first examples that anyone has ever constructed of KKLT-like vacua. These are vacua for which KKLT say, if you chuck in an anti-brane, you should get de Sitter. We're not claiming we've done that. We're not claiming that these are de Sitter vacua. We are claiming these are excellent candidates for which to try and do this. These are the only real candidates anyone has where you have a hope of it working, so let's try it. And I should say, these are the examples for which we're sure Kähler moduli stabilization works, accepting Witten's calculation. We have many, many thousands of other examples with better order parameters for which we're currently checking Kähler moduli stabilization, and yeah, it will work in some of them, not in others, but it's not unreasonable to think we can get like 10 to the minus 5 here and 4 there. And then like that would be a really great example in which to do KKLT. Okay, so that's what I wanted to say. Constructing de Sitter vacua is important. It's, we need to know if string theory has them or not because we live in a de Sitter vacuum. KKLT is one of the best studied ways of doing this. And today I've gone through and shown you the first examples of vacua for which KKLT can be done. All of the ingredients KKLT call for are present in this vacuum. And then people can go crazy. I hope that eventually the dust will settle and people think these are KKLT, maybe not the examples on the last slide, but examples of this type that we can construct will be de Sitter vacua from KKLT. But there's still a lot of things to check before you do that. Okay, thank you for listening.
1 or 2 questions after the 3rd row and beyond. I guess we've had a lot of discussion, so we'll just thank the speaker again. Richard will be around today and tomorrow. Speaker dinner time. So, yeah.
Thank you, everyone.
Stop the recording and the real questions begin.
Who's on Zoom? Who's on Zoom?
Monkey and
I think Austin and the Cornell group. Okay. I saw Maggie, Nyana,
stay on.
Are some of Liam's students.
Well,
the main Liam group has left.